next, we are very happy to have Enrico Herrmann from SLAC, who will tell us about all-multiplicity non-planar MHV amplitudes in super Young-Milstead loops. Take it away.
All right. Can you all hear me all right?
Yes.
Okay, very good. Thank you. Well, let me start by thanking, of course, the organizers and the committee for putting together the first very environmentally friendly Amplitudes conference, and especially for giving me the opportunity to present some of my work that I've been doing together with various subsets of my collaborators, Jake Borgelli, Cameron Langer, Andrew McLeod, and Jaroslav Dranka. In particular, I'd like to share with you the first non-planar all-multiplicity result for scattering amplitudes in super Young-Mills theory at 2 loops. And this talk is based on some work that appeared over the last year in these 2 papers down here, and also on some work that we're hopefully publishing soon. So just to set the stage, I'm sure for this audience, I don't need to motivate why we're interested in scattering amplitudes and what they are good for. Already this morning, we heard some very interesting talks on the relation between scattering amplitudes and collider physics. And later this week, we'll hear more about relations between scattering amplitudes and gravitational wave physics, as well as inflationary correlators. So besides these more practical applications of scattering amplitudes, we also know that scattering amplitudes give us a unique diagnostic tool to listen into the deeper structure of quantum field theory. And just to name 2 of these recent developments, there is the connection that was first discovered in N=4 super Young-Mills theory in the planar limit between these geometric ideas where the buzzwords are Grassmannians and the amplituhedron and other polytopes that we're also going to hear more about later this week. So already in the talks by Benjamin just now and in the talk by Lance this morning, we saw that like there's enormous progress in calculation of scattering amplitudes and related subjects in planar N=4 super Young-Mills theory. And that's due to its large amount of symmetry that we've also heard more about earlier. So at the integrand level, there are these geometric ideas that were also first discovered in this planar N=4 setting. And then we've heard a lot about the integrated results, the full amplitudes by Lance, and now Benjamin. A natural question is, do any of these nice features that we see in this very simplified theory, do any of these features survive beyond this planar limit, beyond this simple theory of planar N=4 super Young-Mills theory? Well, the most interesting or the most natural starting point away from this planar N=4 super Young-Mills is to loosen the restriction on planarity and to consider the fully color-dressed N=4 super Young-Mills theory. And recent years have told us that indeed, beyond the planar limit, there have been interesting structures emerge. We heard from Johannes this morning about non-planar contributions to the cusp anomalous dimension. And there's also 2 works on subleading color corrections to Wilson loops and some generalization of dual conformal invariance beyond the planar limit. So what amplitudes have told us in the past is that for many of these explorations, it's useful to have explicit data, explicit theoretical data of scattering amplitudes that we can then probe and look for hidden structures. So with this in mind, the goal of this talk is to generate exactly such new theoretical data that we can then milk for further explorations. So with that, let me skip to the final result of the final formula that I'd like to present to you. And that is the first explicit all-multiplicity result for the 2-loop endpoint amplitudes beyond the planar limit. So all the results that I'm going to show you today are at the integrand level, so before loop integration. So there will be no transcendental functions and no zeta values in my talk here. So the structure of our result is going to include 2 main building blocks. The first main building block that you see is here shown on the first line of the slide. And the on-shell functions. So they encode all the non-trivial external kinematic dependence of these prefactors of amplitudes. And what I want to mention here is that they include also the full color information. In interest of time in this talk today, I'll focus more on these on the second part of the building block, which are these loop integrands. So these loop integrands kind of incorporate all the non-trivial loop dependence. And so these will be Feynman integral type objects that have non-trivial denominator structures are given by the propagators of these graphs. And on top of that, they have very non-trivial numerators. And what I want to explain in my talk today is like how we constructed this very nice explicit representation for these loop integrands. And then the ultimate end product of our result is the two-loop integrand, which is given as a particular sum linear combination of these f's, which are these on-shell functions, dressed by their appropriate loop integrands. So the takeaway message, or if you want to take one thing away from this talk, is that our formula is basically a correction to the Park-Taylor, the tree-level Park-Taylor amplitude, where we added both color and loops to the Park-Taylor amplitude. That has been such a great inspiration in the field for amplitudes. And hopefully our result can also stimulate further explorations similar to the Park-Taylor amplitude. Okay. So just today I focus on the loop integrands. So just let me mention in one slide what I mean by these on-shell functions. These on-shell functions, as I mentioned, are completely color dressed. And so these funny looking pictures here include both color information, which we address here, which are just products of FABC structure constants times some kinematic factors. And we know in n equals 4 superannuals, even beyond the planar limit for these amplitudes that we're looking at, these kinematic dependent factors are just given by some particular sums of Park-Taylor factors. And about the color structures, I'm sure we're going to hear much more about in Alex Ashirov's talk later in this week. One thing that's important to keep in mind that these pictures here are not all independent, but they satisfy some non-trivial identities that one can derive from certain residue theorems. So with that being said, the plan for the rest of the talk is going to be as follows. First, I'll talk to you a little bit about what I mean by these integrands. Then I briefly review the method of generalized unitarity. I'm sure many of you are familiar with it. Following that, I'll give you a refinement of generalized unitarity, which we call prescriptive unitarity, which avoids some of the linear algebra problems that are associated with the traditional way of setting up generalized unitarity. Relevant for both of these unitarity methods is something associated with a basis of integrands. And one of the most rudimentary information that you can know about a basis is just the size of the basis. What's the dimensionality? So I'll spend some time explaining how you can do a counting of bases. Before then, I'll do a little bit of a cheat and I skip ahead to really tell you, like very briefly, how you can then use these bases, the knowledge of this counting of bases, how to derive like these nice representations that I showed in the beginning of the slides. So let's get started. So it's not hard to see that the generic form of any loop amplitude is given by the following form. You can think of this as Feynman diagram expansion or some unitarity-based expansion, where the loop amplitude is given by some sum of rational prefactors, these AI that encode external kinematic information, colors, charges, and so on and so forth, times these loop integrals. And the non-trivial thing about these loop integrals is that, well, you can give them as integration over all of Feynman's loop variables. And then the integrand is a rational function that has a numerator that can depend on loop momenta and external momenta, and the denominator is given just by products of Feynman propagators. So the key feature of this formula is that the integrand of this object is a rational function on the space of loop momenta. And as such, if you have a rational function, you can expand that rational function in terms of a basis of rational function. And then, of course, the most naive question that you can have is, well, can we count such a basis? Can we construct them and analyze them in a very particular way? And of course, this has a long history that goes under the name of integrand reduction that probably goes back to the work of Melrose in the 1960s, and then probably more familiar to people, Passarino and Veltman in 1979, and many others. So just to set the stage, let me briefly mention what I mean by generalized unitarity. As I already said, we take the scattering amplitude as some linear combination of yet to be fixed coefficients, some AI that can depend on external kinematics, times these loop integrands. And these II here that I'm showing here, they are part of some basis of rational functions. So that's the basis can be arbitrary, as I'll explain later. So the key part of rational functions is that they're completely fixed by the set of its residues. So what one does in these unitarity-based methods to construct loop amplitudes is that one compares residues on the left-hand side of the amplitude to residues of this basis expansion or of an ansatz on the right-hand side. And that leads to a linear algebra problem for these prefactors AI. So what are these residues of field theory? Well, these are given by what are called unitarity cuts, where you set certain propagators on shell. On these unitarity cuts, amplitudes factorize into the product of simpler objects. Ultimately, if you put enough things on shell, the amplitude factorizes into products of tree-level amplitudes. And as such, these residues of field theory are very easy to compute. So all of this more abstract thing that I just mentioned should be very familiar to many of you at the level of one loop generalized unitarity. So at one loop, the basic integrand building blocks that you have are boxes, triangles, and bubbles. And in order to fix their coefficients, their AI coefficients, you can take field theory cuts. So in order to isolate the box coefficient, you take this quadruple cut, where field theory is just a product of these 4 3-point amplitudes given here. So okay, once you have done that, you can ask for the coefficient of these triangle integrals. So the triangle integral, so you have to set 3 propagators on shell. Field theory, the correct field theory value is the product of these 3 tree-level amplitudes. But here it's already the slight subtlety that on this cut, not only the triangle contributes, but also a bunch of boxes will contribute. So in order to get field theory correct in a naive basis, you have to subtract all the contributions from the boxes. And that already leads you to a little bit of a linear algebra problem. And you can imagine that that becomes worse if you put in more loops and more legs. So one thing to keep in mind is that once you're beyond these maximal cuts, these leading singularities, in principle, these cuts depend on some leftover unfixed degrees of freedom. And in order to solve this linear algebra problem, you can in principle pick arbitrary points on these cut surfaces where you set up your linear algebra problem. Okay, so there's two sets of, there's two pieces of arbitrariness. One is the choice of some complete but arbitrary basis, B, of these integrands that you're using. And the second set of arbitrariness is which residues, which places on these cut surfaces you're using to specify the answer. So, and as you can imagine, well, once you have arbitrary choices, you can of course make very bad choices that basically make your coefficients complicated, and also ultimately for higher loop things, make your linear algebra problem prohibitive. So one question we tried to ask in our older work was like, can we avoid some of these complications? And the answer is yes, we can. The way to do it is goes under this name of prescriptive unitarity. So in this, the basic statement about prescriptive unitarity is that these bases of integrands that one would like to try to construct should be diagonalized in a spanning set of cuts. So one takes a spanning set of these field theory residues and then constructs basis integrands that are constructed such that a given integrand is unit on one of the defining field theory cuts and vanishes on all the others in such a way that, well, doing so already diagonalizes the basis, and that avoids some of the linear algebra problems. So for details, you can either look at our paper or there's talks in previous Amplitudes editions, but this is kind of the strategy we're going to follow here as well. So, so once I give you the kind of broad outline of where we want to go, I told you that it's important to have these complete bases of integrands. So before we discuss the possibility of defining nice integrands, a nice basis of loop integrands, we would need to know how many of them are there in the first place. And it's not so hard to imagine that the size of the basis depends on two key factors. One is the space-time dimension, or said differently, the number of loop degrees of freedom that you have in these Feynman loop momenta. The second thing is the power counting. Power counting, I'll say more about this later, is basically you have how many loop momentum dependent factors. So once we have these bases, it's natural to talk about like vector spaces of numerators. And in order to do so, it's good to introduce a little bit of notation. So we know for Feynman integrands, one of the key features that are there are propagators. So in making things more uniform, it's also quite natural to talk about the numerator factors in terms of some generalized inverse propagators. And so for a numerator with a single loop momentum dependent insertion, I denote that by this square bracket L in D spacetime dimensions, which is given by the span over all possible momenta Q of these generalized inverse propagators. And this space is equivalent to something that's probably more familiar to you, which is the span of these things, where I take L squared, all possible dot products of L and unit vectors in D spacetime dimensions, and I'm also including the constant. It doesn't depend on L at all. Just a little bit of notation for people who are familiar with embedding space formalism that might look very similar to you. So one thing that's very easy to count here for this very particular example that I have is the dimensionality of this space. So if you insert a single of these numerator tensors here, the rank of the space, the dimensionality of the space, is D plus 2 dimensional in D spacetime dimensions. Once you start constructing a higher rank numerator insertions, where you basically insert powers of these basic numerator building blocks, turns out that these numerators are given, or the dimension of these numerators are given by symmetric traceless representations of SOD plus 2, and you can count the dimension easily as well. So with that, power counting is actually a little bit tricky, not at one loop, but for higher loops, it's a little bit of tricky. And let me explain why. So in order to do that, I want to do that at a very particular example. We can do that more generally, but for the sake of concreteness, I do what I call 3-gun power counting in D equals 4 spacetime dimension. And that's the case that's relevant for the construction of these 2-loop integrands that I'll show later. So what do I mean by 3-gun power counting? At one loop, it's very simple to see that, well, naively, we have the bubbles. So the bubbles asymptotically at L goes to infinity scale like 1 over L squared squared. And we would say that this violates 3-gun power counting. It scales too badly at infinity. So for 3-gun power counting, we would exclude these topologies. The basic building block for 3-gun power counting is, of course, the 3-gun, the triangle, the scalar triangle, which asymptotically at L goes to infinity scales like 1 over L squared cubed. So that's great. We want these pieces. Then we keep going. We can add integrands that have more propagators. So the box is 4 propagators, which allows us to have a non-trivial numerator factor in order to keep the asymptotic scaling. So if we have 4 propagators, we can insert one of these generalized inverse propagators, and it has the same asymptotic scaling at L goes to infinity as the scalar triangle. So that's great. So as I said, in D equals 4, the space of these numerators is D plus 2 dimensional. So it's 4 plus 2 dimensional, 6 dimensional. And there's a natural way to stratify the spaces, to split the spaces up, where we can split this 6 into 2 degrees of freedom that are truly associated to the box topology. We call them top level degrees of freedom. And 4 degrees of freedom of the spaces are associated with contact terms. So contact terms are terms that are proportional to inverse propagators of the graph. And they lead to simpler topologies. So now that we went from triangles to boxes, one can ask, well, does this terminate, or do we get arbitrarily complicated topologies? And for that, the first thing that we can look at is at pentagons. Pentagons have 5 propagators that allows us to insert a rank 2 tensor of these generalized inverse propagators to still keep the scaling, asymptotic scaling at infinity. According to our rank counting formula, the dimensionality of the space is 20 dimensional. And if we do a similar stratification, it turns out that we can fill up this 20 dimensional basis solely in terms of basis elements that are proportional to inverse propagators. So the statement here is that with the 3-gun power counting, all n-gons where n is larger than 4 and D equals 4 spacetime dimensions are reducible. And furthermore, one can stratify this basis even further, that one can decompose these 20 degrees of freedom into 10 degrees of freedom that are associated to scalar triangle integrands, and 10 degrees of freedom that correspond to the 5 choose 4 boxes with 2 degrees of freedom each. Quite trivial. Going to higher loop, it's a little more, it's more non-trivial to define power counting. But here we advocate for a very graph theoretic way of defining power counting, where one starts with the basic topologies that asymptotically scale like triangles, scalar triangles in all the loop variables. And two loops, there's these two basic topologies, this 212 and 303 topology. They are not allowed to have any non-trivial numerator factor. And as such, their respective basis size is just one-dimensional, the overall normalization of that graph. So then one can add propagators to get higher topologies. And in order to figure out what the numerator allowed space of numerators is for this topology, is one takes the topology and then tries to pinch or collapse all possible propagators in such a way that one ends up to our basic topologies. And down this collapsing path, one keeps track of what propagators one can collapse to write down the numerator factor. So here for this particular example, I have 3 propagators with the red, 3 propagators with the blue. I can collapse 1 red and 1 blue to end up on this 212 graph. So I can write in the numerator something that has L1 inverse propagators in the numerator times L2 inverse propagator. In the same way, I can collapse the central propagator to end up on this 303 graph. So as such, the numerator of this more complicated graph is then given by the span of these two possibilities. And it's a non-trivial fact, or it's a non-trivial exercise to compute the rank of these, dimensionality of these numerator spaces. It's very non-trivial, and we did that exercise. So for this particular example that I show here, it turns out that the dimensionality of the space is 36-dimensional, which you then again can naturally split into 8 top-level degrees of freedom, which are really associated to these graphs, plus 28 degrees of freedom that are associated to simpler topologies. And we can do a similar exercise for all other 2-loop topologies, and we've done that for 3-loop topologies as well. You can do that for different space-time dimensions, for different power counting as well, and we've done this counting exercise. And there's related work by other authors as well that I list here in the references. So now that we've done a basis counting, let's get our hands dirty and actually go to the construction stage. So as I said, I focus on d equals 4 integrands that are relevant for these 2-loop endpoint MHV amplitude topologies in n equals 4 super-Young mills. Turns out there are 6 basic topologies that one need to consider. Some of them are more trivial. They're just products of 1-loop topologies. But here you see you also get these non-planar contributions. And here I'm going to hide a lot of details from you. But basically, following this prescriptive strategy, we found extremely nice and compact representations for the relevant numerators that we have. And just to give you a kind of little bit of flavor of what they look like, for this non-planar topology, our numerators are very compact and they fit on a single line. So here for the experts, these double brackets here are nothing but the chiral traces that are more familiar to maybe people from QCD. So it's just some key factors about these integrands that we've constructed. They have a very smooth transition. So here, these integrands are given for arbitrary Lagranges A, B, and C. So the key feature of our formula is such that they have a very smooth transition as some of these Lagranges become massless or even empty. So here in this particular example, if I let this Lagrange C to become empty, I naively get a double propagator where H is the same as G, this propagator. But our numerator is smart enough that in this limit, the numerator reduces to something that is directly proportional to one of these inverse propagators and kills the double propagator. One more feature is these chiral traces, or these chiral numerators. They have very good IR properties in the sense that they eliminate many of the possible collinear and soft singularities. And as such, these basis elements that we construct here, they should be very nice, hopefully also to integrate. So one thing also that's important for these things is we normalize these integrands to have unit leading singularity. So basically that means that wherever possible, we can go to the maximal codimension residue, and there are these residues of these integrands that we compute are just plus minus 1 or 0. And keeping with the prescriptive nature, we've normalized, or we've defined these integrands to be orthogonal on a spanning set of cuts. And for more details, you can look in our recent work. So let's just come back to the final product. So again, the final product is given by sums over are given by these unshell functions that I've mentioned very little about, times these basis integrants, these loop-dependent basis integrants that have all these nice features that I said before. And you're supposed to sum over all inequivalent contributions of these pictures in order to get the full amplitude. And in our work, we provide actually mathematical code that does all these sums for you as well. So let me just briefly comment on some of the checks that we've done. So our formula reproduces all known 4, 5, and 6 particle amplitudes. So if you restrict yourself to the planar limit where we have access to loop recursions, our formula agrees with the formula that you would get from loop recursions. So you see there's only 6 fundamental building blocks in our equation. And I would like to encourage you to compare that to basically the infinite number of Feynman diagrams that you'd have to compute in another way. We've also made sure that in this formula, once you go to this local expansion, there are certain spurious poles, spurious singularities, and we've made sure that they all cancel. So with that, let me close again with just flashing the formula. So what would we like? What's still left to do, or what would we like to desire? So one thing that might be useful for people who want to actually integrate, and we've heard already some talks earlier this morning about integration. If you want to use dimensional regularization, you have to amend our 4-dimensional integrand with so-called mu terms, these extra dimensional pieces, to make this representation amenable for dimensional regularization. So maybe if you can find like some, for example, mass regulator to regulate the remaining infrared divergences, you might want to integrate this integrand, which has a small set of building blocks. So with this explicit data at hand, I also mentioned something about this non-planar dual conformal symmetry. So here we have more explicit data where we can study aspects of this. And while the data is available, we can look for any other hidden structures. And with that, let me thank you for your attention. And I think if there's any questions, I'm more than happy to answer them. Thank you.
All right, let's thank Enrico.
Anti-rejection medication, I think, from the liver transplant. Occasional random pharmaceutical.
Have any questions?
Anyone? Sorry. Oh no, what happened? Oh, I should stop sharing, maybe.
You're good. You're good. Oh, there's a question from Nima.
Yes, Nima. I don't see you, but yeah,
Oh, sorry. Just a quick question. So, you know, as you know, in the planar limit, those numerators often have very pretty geometric interpretations. There's zeros have pretty geometric interpretations. Is there a good interpretation of the zeros, or is there a geometric interpretation of the numerators that you guys have found?
Well, I mean,
for example, you might drawing your diagram on some surface to make it planar, so that we have dual variables on that surface, say. And so, is it a special point? Is it like one of the special chiral points?
I mean, I don't have an interpretation like maybe this quadrate that you have in mind. But of course, the numerators that we're constructing here, they're also defined to vanish on exactly certain special cuts that we've chosen to define this representation.
Right.
Yes. So in particular, I mean, so if you, hold on, I'm still sharing, right?
Yeah.
If you look at this hexabox A topology, for example, can you see my screen?
Yeah.
So yeah, I mean here, like for this top level topology, you can imagine that if you ask for the set of maximal cuts that this thing has, there's 4 different points where there are leading singularities. And for MHV, only one of them is relevant, where you basically color these 3-point vertices adjacent to the mass SLACs, where you color them all white. And what our numerator does, it's unit exactly on this point, and it vanishes on the 3 other solutions to the maximal cut equations that are not relevant for MHV. So yeah, so that's I mean, okay. That's more like the singularity structure of the integrand. I don't have like a geometric picture like in the sense.
No, I just meant. I mean, I understand that it vanishes in some points in loop momentum space. I was wondering if there was some. I mean, there are some minimal surfaces that you can draw each one of these pictures on to make them planar on that surface, right?
Yes, I agree. I haven't looked at that. No.
Thank you.
Okay. Any other questions, Lance?
So you Nice talk, Enrico. You discussed three-gon power counting, but in the one loop case, it's really box power counting, or you could do it after integration at least. What is the worst, power counting you actually have in these two loop graphs? How many powers of loop momenta in the?
So that's why I discussed three-gon power counting. So the reason, naively, you would expect in n=4 super Yang-Mills, there is something, in the planar limit, it's trivial from dual conformal invariance that you should only have boxes. Analytically, you'd say that it's associated with the absence of poles at infinity. So naively, you would also expect the same property to hold beyond the planar limit. And in certain examples with Svi and Yara in some past work, I checked that. So now to the construction to these integrands, it's actually a bad idea to enforce box power counting, because with that you have to include some topologies that have more than 4L propagators. So that's why we chose to boost the power counting. So basically introduce spurious poles at infinity. The advantage of that is that we can limit ourselves to only integrand topologies with 4L propagators. So it's actually a non-trivial fact that all these spurious poles at infinity that we introduced by having, so whenever you see a box in our representation, you can have up to one loop momentum dependent numerator. And it's a non-trivial fact that all these poles at infinity, they actually cancel. So that was my cryptic remark about spurious pole cancellations.
So
but our representation is
three-gon, four-gon power counting. That's not good enough either.
Pardon?
You need to go all the way to double triangles.
Yeah, that's what we'd call three-gon power counting.
Yeah.
Yes.
So there's nothing with better power counting that can be maintained across all the topologies.
Well, I mean, in principle, you should be able to re-expand. Again, bases are somewhat arbitrary. So what you should be able to do is you should be able to write n=4 manifestly in terms of box power counting. But that comes at the cost that you then have to introduce integrand topologies that have 9 propagators.
Okay.
So for example, in the planar limit, you've seen the nice formula in terms of this double pentagons, which have 9 propagators.
Thanks.
Yeah.
And we have the last question from William.
Hi, Enrico. Can you hear me?
Yes.
So thanks a lot for your talk. It was very nice. So I have a couple of questions. The first one is regarding the dimension you are working in. So you said that, if I understand correctly, everything is in d=4.
Yes, that's right.
Can you do a guess about the dimensions? If you make a decomposition in 4 and the extra dimension, what could happen there?
So I have 2 answers for you. So one is, in this upcoming work that we're doing, we're going to explain how you can incorporate mu terms into this basis counting. Mm-hmm. And so in principle, then you could, once you have this complete basis, you can then look for special points in CADs where you want to specify these mu terms. So the problem is that, like, so all these on-shell functions are very easy to compute in strictly 4 dimensions. So I think you would have probably a less compact formula if you include all these mu terms. Yeah. So, but we haven't. So that's then the more trivial answer to your questions. We haven't looked at trying to incorporate mu terms. No.
Okay, thanks. And the second question, if I may,
yes,
is, well, so far everything is massless. Have
yes.
you tried to do anything with massive particles?
Well, so again, I
know that with the generalized unitarity, you cannot reach that level, but
well, I mean, you can define these cuts. I mean, you can do generalized unitarity for massive particles. Well, the building blocks that you'll have, these products of tree-level amplitudes and stuff, are going to be more complicated. But I mean, also this integrand construction, a priori, the mass doesn't play much of a role. You can similarly count like these bases of rational functions, including masses. that, but that's a part of our upcoming work, hopefully appears sometimes in the next few months or so. And so yeah, masses a priori aren't that big of a problem for these integrands here. It's like, well, the problem here is that you will get a representation for an amplitude. The problem is that it might not necessarily be a nice one. So I guess like, so the takeaway here is for nice amplitudes, as the one we constructed here in n equals 4 various masses, you get nice representations. It's not a priori clear that for an arbitrary kind of garbage quantum field theory, you'll get a nice representation. That's certainly not true. And especially after integration, you know that masses lead immediately to more complicated functions.
Okay, thanks.
Very good. Let's thank Enrico once again.
Thanks.